Hello, we are the URI Robotics team, and the name of this project is RoboToy. Our two technical directors for this project are Dr. Paolo Sagagno and Cameron Amaral. Our team is composed of two computer engineers, Luis Medrano and myself, Kyle De Silva, along with two electrical engineers, Chris Gulivas and Noah Doeg. The company we worked with was the URI Intelligent Control and Robotics Lab. This lab is an interdepartmental research group here at URI who focuses on industrial automation, soft robotics, and human and robot interaction. The project motivation was to promote and expose kids to the computer science field. This exposure allows for the best STEM education in Rhode Island and will also allow for underrepresented groups in the STEM fields to have this experience. When looking at the tools developed throughout K 12, they are only fully developed in 6 through 12 and not K 5. Our anticipated best outcome for this project is a fully functional prototype for a single robotic kit, which will be distributed to classrooms around Rhode Island. This robotic kit will include a ground robot and command blocks as pictured in this slide. The ground robot will be a 3D printed robot with an Arduino Mega and motor shield within to program. The command blocks will allow the kids to give the robot commands such as forward and reverse. Some sensors included will be bumpers and an ultrasonic sensor. As a team, we have been able to create a push button array with 8 rows of buttons, a DC motor control, which programs the robot to move, an ultrasonic sensor, which will cause the robot to stop if there is an object detected, the robot chassis, and power regulator to regulate the power needed. With our project, we have a great economic impact, as this will allow students to understand modern technology, which a lot of high-tech companies need. Our project will also specifically allow Rhode Island students to continue their education with this modern technology and will make them even more employable. With this being a URI project, this shows how dedicated URI is to helping Rhode Island students to get the best education they possibly can. As I have mentioned before, I am Kyle De Silva, one of the computer engineers on this project. My main focuses on this project include soldering and Arduino coding. On this slide, we are looking at the overall block diagrams for the project, which are all centered around the Arduino Mega. One of my main accomplishments in this project include the binary shift of the button array. When creating the commands, we determined that we can create the first 4 bits of the 8-bit string as the commands, and then the last 4 bits as the amount of iterations. In order to do this, the buttons are all connected to port C of the Arduino Mega. This allows us to easily read in all 8 bits with one line. In order to read the last 4 bits, specifically, I had created a code to use the mod operator, which will do the variable of the 8 bits, mod 16, which will give us those 4 bits. Then to find the first 4 bits, I used shift right and shifted the string right by 4. With these two operations, this allows us to have two variables where one is the command and the other is the amount of iterations. Another key accomplishment that I have done throughout the project is helping soldering the push button arrays. As pictured on the left, you can see the top view of 2 rows of buttons and MOSFETs used in part of the overall button array. And on the right is the bottom view, including some additional wiring needed to be added. When implementing the start button, we had to make 2 separate methods to implement this. When I first implemented it, I was using 2 if statements. The main if statement was to change the state variable, which is originally set to low to show the button was not pressed. But once the button is pressed, it changes to high. And then the second if statement becomes true, which will then turn on the motors depending on if the last state was high or low. Looking forward to the spring semester, I am planning on continuing to work on the code to implement a speaker as well as LED lights to show which row is being read in by the robot. I also want to help with soldering our final PCB. We will now move on to our next speaker, Luis Medrano, who will continue on talking about his implementations to the code.
Here, we can revisit the block diagram to remind ourselves the ultimate objective for this project. Now that we've revisited the script, we can dive into the following key accomplishments for the software portion of the project. One of the key accomplishments is configuring the DC motors and scripting the binary array into opcode and iterations via push button array on the board. For the binary array, I would distribute the first 4 bits to represent what specific operation it would execute. The lower 4 bits of the array would represent the number of iterations to execute said operations. in X amount of times. The DC motors would adhere to any instruction that the given opcode would represent in the source code. The instructions can be written as going forward, reverse, turn left, turn right, and brake. The following key accomplishment involves adding the start button function as a subroutine. Though one of my teammates wrote a different method of using the start button, I converted the program into a subroutine that can be called into the main function. If the button is pushed while the robot is reading and executing commands, it will trigger the robot to halt. On the other hand, if it's pushed while the robot is in stasis, it will trigger the robot to move. The next key accomplishment is the implementation of the ultrasonic sensor component upon the Robotoy kit. With this annex device, we can program it to scan and detect neighboring objects that can trigger a signal. In other words, if the robot detects an object 10 centimeters or less, it will completely halt the operation it would currently execute. Now that we've gone through describing my feats, here are the targeted goals for the spring semester. I will implement a full binary array and operation command set so that the robot has the full capability to perform on all potential commands given from the blocks. We would like to append a speaker upon the robot as a component that would be called within the instruction, along with other potential gadgets like a robotic crane. Now let's immerse to the next member of the Robotoy team, Chris Glebus, with a major of electrical engineering and a math minor, holding the technical responsibilities of circuit design, printed board assembly, developing the power regulator, soldering components, and testing the hardware for the Robotoy kit.
I was involved in the development of the push-button array and power regulation system. For my individual technical contributions, my main focus was on developing the push-button array. This is the part of the Robotoy which translates the physical addition of the blocks into the language the Arduino can understand. Our prototype Robotoy has 8 rows of 8 buttons. The columns are shorted together so as the Arduino cycles through each row, the output is read at the front of the PBA, sending the 8-bit code to the microprocessor to be read in our program and translated into commands for the Robotoy. Initially, the plan was to use an Arduino Uno as opposed to a Mega board for cost concerns. Thus, the PBA was designed with MOSFET control and an external multiplexer. However, with the implementation of the Arduino Mega and the swath of pins available to us, the circuit could be even further simplified to remove the need for MOSFET control completely. Taking advantage of the appropriate hardware for the task has made the design of the entire project much simpler. Several versions of the push-button array were made, both on breadboard and soldered on a protoboard, as shown here. Additionally, when we were refining the prototype, a PCB was designed which will make the final product look professional. Several versions of the PCB were considered, including employing either through-hole or surface mount components. After some cost-benefit analysis, the cost to produce each design was about the same. It was decided that even if a through-hole design was slightly more expensive then, the benefit of being easier to solder makes it both easier to produce and opens the possibility of having students be involved in building the Robotoy, teaching them valuable soldering and circuit construction skills. My other main contribution was designing the power regulation system. From the start, it was decided that the Robotoy would not be using lithium-ion batteries, as there is some risk of combustion, especially at high current operating conditions, which may be reached under heavy motor stress. Instead, the Robotoy was designed to use AA batteries by the suggestion of Professor Stegano. To use a reasonable number of batteries while also obtaining a useful voltage, there was a boost converter IC to turn the 7.5 volts from the input to above 14 volts to be fed into the linear voltage regulator ICs shown on the right. These ICs take an input voltage of between 14 and 35 volts and produce a stable 12 volts and 5 volts respectively. The Arduino board is supplied with 12 volts, and then the 5 volt supply is available for any other low voltage circuit that may need it. The Arduino does have its own 5 volt supply, however, for the sake of reliability, the redundancy was implemented. Looking to future developments, my main focus is going to be on making the Robotoy more presentable, professional, and interactive. Some ways this will be achieved will be by commissioning a PCB to clean up the push-button array, including LEDs for visual interest, and finishing the power regulation circuit. As of now, extra batteries are necessary, and the boost IC has to be bypassed to enable an independent Robotoy. In the spring semester, I plan to focus on finishing the power supply and making sure the Robotoy can function as an independent unit. I would like to take the time now to introduce designer 4, Noah Doak. Noah is an electrical engineering major with a math minor. Noah has been instrumental in bringing the Robotoy to life, being responsible for 3D modeling and printing the chassis. Please give your attention now to Noah to discuss his individual technical contributions.
As mentioned, my primary focus was getting the hardware fitted into one kit. As it being the first prototype chassis, we needed access to the hardware, while leaving enough room for everything we needed, plus a little extra room for any bumps in our journey. Here's a side view of the chassis modeled in Fusion. It was printed into 2 parts to make assembly and printing easier. At its core is the Arduino Mega. The initial concept required the smaller Arduino Uno, so I made space with mounting holes to accommodate one or the other. At the front or left side of the image, you can see a bumper. I'll discuss a little more on that later. At the top are many locking points for the coding blocks, the blocks that contact the buttons. Button arrays resist being pressed, and locking them down keeps the buttons active. Towards the upper right is the start-stop button. The button just ensures that the coding blocks don't activate before you're done placing them all. Also, you can shut off the robot in the middle of its operation. The last thing you can see in the image is a motor on the back of the chassis. There are 2 motors that follow most of the commands for the button array. Once it was printed, we fitted 4 push-button arrays, each carrying 2 rows of 8 buttons. You can see 4 arrays sitting on top of the 2 rails printed as part of the chassis. Right below that is the blue Arduino Mega. Here you can also see the start-stop button. The coding blocks were 3D printed with a hole passing through. The hole would allow for a rod to slide through the chassis and block in order to lock the 2 together. At the bottom of the block are silicone pins. Each pin is between the block and the button it is pressing. The compression from the silicone allows multiple buttons to be activated within a row. Without it, a single difference in button heights make it impossible for a flat block to press multiple buttons. On each corner of the chassis is a push button, 2 buttons per bumper. The 2 hooks slide the bumper into the chassis, making it difficult for the bumper to fall out. On the inside corners of the bumpers are triangular extensions that make contact with the buttons. If the bumper is hit from the front or corner, a button will be activated and cause the Robotoy to stop or change direction. In the spring, I plan to work towards building 1 large push-button array containing the 8x16 button requirements for the project. I also plan on building a power regulator that functions with AA batteries. A new chassis has to be made for the new button arrays, as well as to make the form factor smaller. Finally, the coding blocks need to be redesigned to become simpler to use. To summarize our remaining challenges for next semester, our team hopes to finish building a power regulator, build more push-button arrays, model a new chassis, improve the coding block design, and add indicators like a speaker and LEDs. On behalf of the Robo team, I would like to thank Dr. Paulo Scagno, Cameron Amaral, and Dr. Harris Sunak for all their time and effort towards helping our team succeed in this capstone project.